See, in this class, we will see about or we will discuss about the fifth unit, that is state space analysis. See, in the first 4 units, we have discussed these things, right? How to know the output of a system if you give some input like step input, right? Parabolic input like that, right? So, but in this 4 units, what we have assumed is the system is a linear system. By assuming the system as a linear system, then we are going to build or we develop the different methods to obtain what is the output and what is the frequency response of the system. All these things we have studied, right? But how to analyze the nonlinear system or time invariant system, right? So to analyze such systems, the basic transfer function approach is not sufficient, right? So what are the things we have seen in the first 2 units or 3 units? So every time we have to get the output means for the system we have to get the output means first what we have to deriving, we are deriving the transfer function of the system, right? So after that one we will get the output y is equal to transfer function into input. So that is, there is a transfer function approach. So if you want to analyze the system in transfer function approach, that is applicable only for the linear time invariant systems, and right. So that is the basic definition of the transfer function approach is used to analyze the systems, but that system should be linear system and also the system is time invariant systems. So for those systems to analyze or to study those systems, we are using the transfer function approach. So whereas coming to the nonlinear system, I want to study the nonlinear system or I want to study the time invariant system, right? Right. So for that one, the basic transfer function approach is not sufficient, right, to analyze the system. So for that one, we are using the state space analysis, right? See, that is the transfer function approach is used to analyze the system, right? But the system should be linear and time invariant system. But for nonlinear systems and time invariant systems, we are using the state space analysis, right, to understand the system behavior, right? And also the important point is up to now what we have discussed is we are giving some single input like step input or ramp input, and we are observing the output y is equal to h of s into x of s, right? So that is for single input only we are using the transfer function approach, right? So there are multiple input multiple output systems, right? Suppose you consider the car engine. So for the car engine, at a time you are giving the inputs from brake, right, accelerator, and all these things, right? So multiple input and multiple output systems are there, right? So to understand or to analyze the output of that system, right? So by using transfer function approach is not well. If you use the state space analysis, you can analyze the system very. You can analyze the behavior of the system, right? So that is for multiple input and multiple output systems, we are using the state space analysis, right? So the point here is this is the difference I have written between the transfer function approach and the state space analysis approach, right? So why we have to go for the state space analysis? Why we have to study the fifth unit, right? So the basic point is the transfer function approach is only suitable for linear time invariant systems, right? And it is generally suitable for single input and single output system, right? So whereas the state space analysis approach is suitable for nonlinear systems and uh, time invariant systems as well as multiple input and multiple output systems, right? So that is the main point you have to remember. And the other important point is here the internal variables cannot be feedback in transfer function, right? Internal variables means here we are talking about the state variables, right? So but in a state space analysis, state variables can be fed back, right? So that is the basic point why you are studying the state space analysis. So for studying the state space analysis, so this is the basic representation of any system, right? See, the state space analysis, we have multiple input, multiple output system I have considered here, right? So MIMO system, it is multiple input, multiple output system. See here U1, U2, UM are the multiple inputs and Y1 so on up to YP are the multiple outputs, right? So now what about this? U is the input, Y is the output. Now what about X1, X2 and Xn? This X1, X2 and Xn are the variables, right? State space variables, right? So these variables define the system behavior. That is the point here. So how to model this multiple input, multiple output system by using mathematical equations, right? So for that one, so any multiple input, multiple output system can be written by using two important equations. One is state equation and another one is the output equation. See here, what are the meaning of states means here? Observe here, suppose it is the, let's consider this is the car, right? Let us consider car engine, right? So X2 is acceleration, and x1 is the velocity. Let us consider, right? So the acceleration, the velocity depends upon the acceleration, right? So that is the one state variable is depends upon another variable here, right? So that is the point here we have written here. So the state equation gives, see here, x dot indicates the derivative of x is equal to linear combination of ax plus bu. What is u here? Input, right? X is the states, right? See that is, see uh, suppose it is, let's consider the position of the car is, let us consider 2 meters distance. If you do the derivative of the position, what you will get? Right, you'll get the uh, distance, and again we are going to derivative, we are getting the acceleration. So that is this, what you are understanding this one is x1 x2 are nothing but the these variables, position, distance, acceleration, and you know this one. So x dot derivative of some something is equal to, it is a combination of different variables, right? So that is the point you have to remember these equations, right? So the point here is to understand the state space analysis, or to write a mathematical model of the system which is of multiple input and multiple output. We are going to write two important equations. First one is the state equation and another one is the output equation. So what is the state equation? State equation is nothing but the relation between the, see, derivative of the state variable x is equal, see here x is a matrix, right? So here x dot derivative is equal to ax plus bu, where u is the input, x is the state variable. X dot is the derivative of the state variable, right? So there is the state equation, and next one is the output equation. Suppose I am giving u1 and u2 two inputs at the same time for the system. So what is the output y1 and y2 for that system, right? So that is here y output can be obtained as a c into x plus du. That is the output depends upon the state of the system, present state of the system, and also inputs of the system, right? So suppose if the car is at 10 kilometers distance, right, then it will reach in what time? If the car is in 1 kilometer distance, it will reach in what time? So that depends upon, that is the output depends upon, the time depends upon the input what we are applying, that is the acceleration, and also the state variable, right? At what position initially it will be there, right? See, the point here is for the transfer function, there is a one important difference here. See, there are two important differences for the state space analysis and the transfer function. Transfer function works for linear time invariant systems, whereas state space analysis works for both linear, non-linear, time variant, time invariant, single input, single output, multiple input, and multiple output. So for this one, we are in the state space model, whereas transfer function only linear, time invariant, and single input, single output only it will works. And the second point is, right, the transfer function initial conditions assuming as a 0, right? Whereas for state space analysis, we can assume the initial conditions also, right? So initially I applied this much acceleration. Now if I apply some more input, what will happen from that point? So that is the point here, right? So what is x here? State variable, right? So that is the output depends upon the final output depends upon the. So at present, what is the state of that one? What is the state of that acceleration, or what is the state of that position? And also, and what is the input you are applying? So that is the output depends upon the state x and also u input applied, right? Whereas state equation depends upon the x dot equal to state, present state, and also inputs. So these are the two important points. See, to write any, to solve any problem, you have to remember these two important equations: state equation and output equation. State equation gives the relation between the derivative of state variable x dot is equal to ax plus bu. That is, it is a function of state as well as input. Whereas output can be equation can be written as, that is, output is a function of y is a function of y is equal to x. That is the state of the system x, and also plus inputs what you have applied, right? So based upon those things, output is depends, right? So that is x dot is equal to ax plus bu and y is equal to cx plus du. These are the two important equations to represent the any system in state space model representation, right? State equation is x dot is equal to ax plus bu, and output equation is y is equal to cx plus du. And what are x here and what is a, b, all these things here, right? Right. See, here A, B, C, D are the matrices. So we'll see while doing the problem what are those things, right? And what is capital X here? Capital X is the matrix. which is a input matrix, right? Input matrix or input. I mean, sorry, U here. U is the inputs, right? So right. So U is the input matrix, right? Or input vector, where U is equal to U1, U2, so on up to UM are the inputs you have considered. So that vector U1, U2, so on up to UM. Right. What is why? Why is the outputs? So here outputs are also multiple outputs, right? So that's why outputs are Y1, Y2, so on up to YP. And X is the state vector. How many states are there, right? In a system. See, generally, while doing the problems, we can assume that the number of states is equal to order of the system. So that thing we will see while doing the problems, right? So as of now, we have to remember this one. See, any system can be represented in state space model by using two important equations. One is state equation, another one is the output equation. What is state equation? It is x dot derivative of x is equal to ax plus bu, and output equation y is equal to cx plus du. Remember this point. Now we'll see some important problems, right? Or how to write the transfer function for multiple input, multiple output system. All these things we can see, right? Okay. Right. So first of all, I am considering the system like this. So this is the differential equation given. See, what is this differential equation gives? This differential equation is nothing but the system. See, what is u here? What is u here? U is the input. Y is the output, right? If you do the derivative for this equation, what will happen here? It is y triple dot is three times derivative, right? Y double dot is 2 times derivative, right? Time derivative. So if you can write in this in terms of S domain, say u of s, 6y of s, 11 sy of s, 6 s square y of s, s cube y of s, right? So now you can write this one y of s by x of s is equal to 1 by s cube plus 6s square plus 11s plus 6y. That is nothing but the transfer function of the system, right? The transfer function of the system is general right here in S domain. It is represented in the differential equation, right? So that is, this is a system or transfer function they have given, right? So I'm saying here indirectly they have given the transfer function of the system. Now what you have to do, you have to write the state space model for that actual system behavior, right? So how we have to write that one, right? So the question is obtain the state space model for the system described by y 3 times derivative plus 6y 2 times derivative plus 11y times derivative 1 time derivative plus 6y plus u is equal to 0. This is the problem they have given. Now we have to write the state space model for this differential equation, right? See, the main important point here is, first of all, you have to assume the number of state variables for the system, right? Why? Because state space model representation is x dot is equal to ax plus bu, right? And y is equal to cx plus du, right? So there, what is x? X is nothing but state variables, number of state variables x1, x2, so on up to xn. Now, how to choose that number of state variables, right? The point here is, see, what is the order of the system? It is the highest derivative, that is 3 here, right? See, this is the 3 is the highest derivative in this total equation. That's why if the system order is 3, then you have to choose 3 state variables, right? That is x1, x2, x3 you have to select. Why I have select only 3? Why? Because the system order is 3 here. What is the order of the system? It is the highest derivative of the given system, right? That is 3 times derivative is the highest derivative of this system. Now, 1 second. Hello, sir. అవును సార్ చేశాను సార్. అంటే ఒక ఇద్దరిది ఎడిట్ చేయాలి సార్ అందులో. ప్రెజెంట్ క్లాస్ తీసుకున్నా సార్. నేను ఒకసారి మీకు వాట్సాప్లో మెసేజ్ పెట్టమంటారా సార్? మాది అయిపోయింది కానీ అది అక్కడ ఉన్న వాళ్ళు ఒక 2 మెంబర్సే ఉంది సార్. నేను ఒకసారి మెసేజ్ పెట్టమంటారా? అలాగే సార్. ఓకే సార్, ఓకే సార్, ఇప్పుడే పెట్టేస్తాను సార్, వాట్సాప్ పెట్టేస్తాను సార్. థ్యాంక్ యూ. Right. See, 1 second. మా ప్రాబ్లం కనిపిస్తుందండి మీకు? ఎవరన్నా ఒకటి చెప్పండి నాకు.
కనిపిస్తుంది సార్.
ఇప్పుడు కనిపిస్తుంది కదండి. రైట్. See, I think all of you understanding now. See, that is a system transfer function is given. Now you have to write the transfer function of the system into state space model representation. So for that one, first what you have to consider, what is the order of the system you have to consider. The order of the system is here, what is the maximum derivative, right? That maximum derivative is the decides the how many state variables we have to choose for the representation of that system, right? So here the maximum derivative is 3 times. So that's why here the state variables are I am taking 3. So that is x1, x2 and x3 are the 3 state variables we are taking, right? That is the important part you have to remember, right? So next, so after taking this one, I have to write here. So this y, output y is equal to x1 I am writing, right? See, that is I am defining the output y as a some state x1, and y dash means derivative of that one, derivative of or x2. I am writing x2 is equal to derivative of dy by dt, right? One second. X are the 3 state variables, right? Now I am defining x1 is equal to y, and x2 is equal to dy by dt, and x3 is equal to d square y by dt square, right? And if it is x2 is equal to dy by dt, then we can write this is nothing but y dash. But here if you do the derivative of this y, then it is nothing but x1 dot. Why? Because if you do both derivation for both sides, here y dot is equal to x1 dot. So that is here x2 is equal to x1 dot. We are assuming. See, these are our assumptions, right? That's why the state model may be not single. Transfer function for the system is single, but for the state variable or state space analysis, the state space model representation is not single. You can represent the system in different number of ways, right? That depends upon the what are the variables you are taking, x1, x2, x3, right? So x2 is equal to x1 dot. So x3 I am writing as d square y by dt square. See, that is nothing but y double dash, right? If you do the derivative of this y dash, it becomes y double dash. So it is equal to x2 dot, right? All of you understand this point. So like this, we are assuming the state dependencies, right? So that is what is x1 actually. See, you know this one. So what is the position and velocity and acceleration? See, if you do the derivative of this position, velocity derivative, acceleration, right? So that is one depends upon another here, right? So that's why here x2 is equal to x1 dash means acceleration is equal to derivative of the velocity. So that is the point here, remember, right? So what are the states here? The velocity and the acceleration. That is the point. So what is x2 here and what is x1? Those are nothing but the velocities. If y is the displacement, right? So like that, we are assuming the system behavior as x1, x2, x3, where x1 is equal to y, x2 is equal to x1 dash, x3 is equal to x2 dot, right? So that is the point you have to remember. So after that one, you can substitute here y is equal to x1 in this equation, and y dot is equal to x2. Why? Because in this equation, what are the things we have? Y dot, y double dot, and y triple dot, right? So I can write y is equal to x. Now y dot is equal to x2. You can write from this here. Y dot is equal to x2. Y double dot is equal to x3. Y 3 times derivative is equal to x3 dot. Right. See, why I am writing all these things means you already studied to represent the system in state space model. You have to represent that one in 2 mathematical equations. One is x dot is equal to ax plus bu. That is, we have to write the mathematical equation in terms of x dot. X dot is equal to ax plus bu. And also another thing is you have to write y. Y is equal to y is equal to cx plus du, right? So in that terms you have to write. So to write that one, what you have to write? If you substitute this y is equal to x1 here, yeah, y dot is equal to x2 here, y double dot is equal to x3 here, and y triple dot is equal to x3 dot, and you can write. So x3 dot is equal to x3 dot means this one. This one is equal to, you can take this one to this side, right? RHS. It is equal to minus 6x1 minus 11x2 minus 6x3 minus u. Why? Because here y is nothing but, see, y is nothing but x1. So that's a minus 6x1. and y dash is nothing but x2. So I have written that one as x2 into 11, right? And minus 6x3 here, right? So that is, see, all these things are easy. Just by seeing this equation, you can write the answer. By seeing this equation, the answer is minus 6x1 minus 11x2 minus 6x3, right? Minus u. It is nothing but x3 dot. See, why I am writing this one? X3 dot is equal to. So by seeing this equation, it is in the form of x dot is equal to ax plus bu form by using this equation. So that is this equation, this second equation will use the state equation. That is how one state will depend upon the another state. So like the example what I have taken, how the acceleration depends upon the velocity change. It is nothing but derivative of velocity is nothing but acceleration. Right, if the velocity is changing, automatically the state of the engine is changing. Why the state of the engine is changing? The acceleration of the engine is changing, right? So there's a point here, that is the depends upon the acceleration depends upon the ax plus bu. So this is the state equation, how one state will depend upon the another state. So now we got this one, and then again what you have to write, you have another equation called output equation. Right, to represent the state space model, you are representing two things. First one is the state equation. This is the state equation plus bu form, the second one. And now what you have to do? You have to do the you have to do the so you have to write another equation for output equation, that is y is equal to cx plus du form. How we have to write the y is equal to cx plus du form from this equation? So that is, so you know this one, the state equation what we have defined is x1 dot is equal to x2 dot is equal to x3 dot is equal to minus 6x1 minus 11x2 minus 6x3 minus u. See, all this comes under x dot is equal to ax plus bu form, these things, right? X dot is equal to ax plus bu, where x dot is equal to x1 dot, x2 dot, x3 dot. See, capital X dot is nothing but a one vector, wherein x1 dot, x2 dot, x3 dot are the elements of that vector. That x is equal to ax, right? X is nothing but x1, x2, x3 plus bu. So here one u is there, here no u is there for these two equations. So these three combinedly we are saying there's a state equations. So we'll see in detail how we are writing that one. Next, the output equation is nothing but y is equal to cx plus du. Here already we have defined y is equal to x1, right? Y is equal to x1 we have defined, right? So that is the output y is equal to cx plus du. D is 0, no u is there here. So d is 0. And cx1. So now these three comes under the state equation, right? And this is the output equation, right? Now how we have to write this one in the standard form? What is the standard form of the state equation? X dot is equal to ax plus bu, where x dot is the vector of x1 dot, x2 dot, x3 dot, and x is the vector of x1, x2, x3, and u is the vector of u1, u2, u3, right? So on, right? So that is x dot is equal to ax plus bu. I have to write now. So from this one, x1 dot is equal to, right? X1 dot is equal to x2 we have. So that's why I want to multiply this 1 into x2 here. So that's why I am writing 0, 1, 0. So x1 dot is equal to 0 into x1 plus 1 into x2 plus 0 into x3. So that is equal to x1 dot is equal to 1 into x2 you'll get here plus 0 u. So that is the first equation you got. What is the first equation? X1 dot is equal to 0 x1 plus 1 x2 plus 0 x3. That is x1 dot is equal to x2 plus 0 into u is 0. So that is x1 dot is equal to x2 you got. Next, x2 is equal to x3. X2 dot is equal to x3. So x2 dot is equal to x3 means now 1 I am writing here, right? Why? Because 0 into x1 plus 0 into x2 zeros, 1 into x3 you require. That's why 1 I am writing here, right? So x2 dot is equal to 1 into x3 plus there is no u in this term. That's why I am writing 0 here in the matrix. And similarly, x3 dot is equal to minus 6x1. So minus 6x1 minus 11x2. So that's why I am writing minus 11 here. Minus 11x2 minus 6x3. Right, I'm writing those things, and minus u is there. That's why here minus 1 is the matrix, right? So that is x3 dot is equal to minus 6x1 minus 11x2 minus 6x3 minus u, right? That is a state space model representation. Next we are at the output equation. Y is equal to cx plus du is the form. So y is equal to, so here only x1 is there. That is 1 into x1 plus 0 into x2 plus 0 into x3. That is nothing but only x1 plus no t term is there. So it is 0. no term is there. So D matrix is completely 0. So these two equations or these two matrix form is nothing but the state space model. That is the transfer function given in this differential equation form, that is 1 by s cube plus 6s square plus 11s plus 6. Right. For the transfer function, we have represented in the state space model like this. The mathematical representation of the same system. Right. So now we can try for this system. Y triple dot plus 4 y double dot plus 2 into y dot. That is, dot means single time derivative, 2 times derivative, 3 times derivative is equal to 10. You can write the same thing. X1 dot you will get x2, x2 dot you will get x3. See, from this equation you can directly write this one. Right, x3 is equal to minus x1 minus 2x2 minus 4x3 plus 10u. So from this one you can write this is the state equation, this is the output equation. You'll get the matrices here. X1 dot is equal to, here you get x2, here we got, right? So here I am writing x2 here, I1 into x2, and x2 dot is equal to x3, 1 into x3 here. X3 dot is equal to minus 1 minus 2 minus 4 plus 10u. So that is the state equation for this problem. So these two are the important problems. What we are doing here, how to write the state space model for the differential equation. What is this differential equation giving you? This differential equation is giving you the system behavior, right? So up to now what we have seen the difference between the transfer function approach and the state space approach. The transfer function approach, it is only suitable for linear system and time invariant system, and also for single input single output system, whereas state space analysis is applicable for linear time invariant system, linear, non-linear, time invariant, multiple input, multiple output systems, right? And also the important point what I have written is the initial conditions assumed are 0. That is the definition of the transfer function, right? So to apply the transfer function, the initial conditions assumed should be 0. But if you want to include the initial conditions also, what is the meaning of initial conditions? Already the car is at 10 kilometers. That is the initial distance is 10 kilometers. You have to consider while processing the output, right? To find the what is the distance at the later stage after applying some acceleration, right? So to understand those analysis, that is with initial conditions we have to analyze, means for those systems you have to use the state space analysis. For those systems we are not able to understand by using transfer function approach. That is the two important point. So later we have seen how to convert the given differential equation of a system into state space model. That thing we have seen. So next we will see the how to write the state space model for the transfer functions given. Right, here we are using the direct decomposition method. Direct decomposition method we are using here. Right, so that is the next concept is how to write the state space model for the transfer function. Previously what we have done? Previously differential equation icharu. Then we have written the for the differential equation we have written the state space model. Now here they are directly given the transfer function. Now we have to derive the state space model for this transfer function. But what is the approach they have given in the exams? In the exams you have to very carefully observe what is the method they have given. They have given the direct decomposition method here. So by using this direct decomposition method, we have to convert the given system transfer function into state space model. How we have to write? So the first step is, so I am taking the first problem, 5s square plus 6s plus 8 divided by s cube plus 3s square plus 7s plus 9. Here it is the numerator and this is the denominator, right? So first of all you have to write in the decomposition form this equation. What is the decomposition form is? You have to separate the numerator and the denominator. Denominator is 1 by s cube plus 3s square plus 7s plus 9 into 5s square plus 6s plus 8. So it is numerator and it is denominator. So like this, first of all you have to consider here. After that one, that is the first step, right? The denominator in decomposition form. So this is the decomposition form. So after that one, next, so you have to write the block diagram model, right, of this denominator, right? So the denominator contains 9 here, the coefficient constant, 7 as the s coefficient, 3 as the s square coefficient, 1 as the s cube coefficient. So to write the model, you have to use these coefficients. 9 is the coefficient here. Right, so to write the coefficients of here, constant is 9, yes, coefficient is 7, is 3. Now observe here the highest order in the denominator is 3 here. That is the highest power is 3 here. So based upon this highest power 3, here we are choosing 3 1 by s blocks first of all.
3. Why I am choosing only 3 1 by s blocks? 1 by s blocks only 3 means here the denominator highest power is 3. That's why I am using 1 by s 3 important 3 1 by s blocks here. Right. After that one, so the s square coefficient is written like this as a block and giving us a negative feedback here. And s coefficient 7. So that's why the s coefficient 7 is giving feedback from here to here, negative feedback. Observe here, it is a negative sign, it is negative feedback. And the next one is s square coefficient is 3. So giving, I'm sorry, s square is already completed, s is already completed, and the constant is 9. And you are given the 9 as q. See, if you solve this one by using the block diagram reduction technique, right? Block diagram reduction technique, if you reduce this one, you'll get the result here. Output is equal to 1 by s cube plus 3s square plus 7s plus 9. Now we have written the block diagram for 1 by s cube plus 3s square plus 7s plus 9. Now, but along with this term, we have 5s square plus 6s plus 8 as a numerator, right? So for that one, so we have to add some extra blocks to this diagram so that the numerator term will also appear, right? So for that, what we have to do, the second step is for this diagram, how we have to write the numerator terms. So the numerator term is included in the above diagram by taking the numerator s square coefficient, that is 5. Right. See, this numerator s square coefficient is 5, numerator s coefficient is 6, numerator constant is 8. Right. So s square coefficient is 5, s coefficient is 6, and constant is 8. So now how I am writing, right? So to this diagram here I am taking here at the end, I am taking it as a x1. If it is x1, so it is x2. Right. See, it is 1 by s means integration. 1 by s means integration. If it is x1, right, integration x1, right, it is nothing but x1 dash also. Why? Because x1 dot is supplied to the integration, output is x1, right? If it is x1, it is x1 dash, right? So first of all, assume it is as x1 and here x2 and here x3. Assume that if it is x1, it is x2 and it is x3. Automatically, if it is x1, it becomes x1 dash. If it is x2, automatically it becomes x2 dash also, right? So what is the meaning here? It is x1, x1 dash, x1 dot is equal to x2, x2 dot is equal to x3. So like this, we are assuming the state variables of the system. After this one, so write the constant here, constant term 8 here, and then so from here we are write the constant and we are to the one adder, and next from here we have to write the s coefficient to adder. And next from x3, you are writing the s square coefficient 5 and to the adder. So if you simplify this one by using the Boolean block diagram reduction technique, you will get this transfer function 5s square plus 6s plus 8 by s cube plus 3s square plus 7s plus 5. Now for this diagram, you have to write the state space model easily. So how we write the state space model? See, observe here, output to equation y. Output y is equal to y is the output of this adder, whereas the inputs of this adder is 8 into x1 plus 6 into x2 plus 5 into x3. That is the output equation. That is y is equal to 8x1 plus 6x2 plus 5x3. So you got the output equation. And what are the state equations? State equations are x1 dot is equal to x2, x2 dot is equal to x3, right? And what about x3 dash? X3 dot is nothing but the output of this adder, right? That is x3 dot is equal to, see here it is, right? 9 into x1 minus 9 into x1, and also here minus 7 into x2. See here x2 minus 7 into x2 minus 3 into x3. It is nothing but x3 dash. So from this diagram, I am writing these three equations, right? So these three equations, using these three equations, you can write the state space model, and by this equation, you can write the output equation, right? So that is by using this one, we can write x1 dot is equal to x2. That's why x2 I have written 1, x2 dot is equal to x3, x3 I have written 1 here, and x3 dot is equal to minus 9, minus 7, minus 3, minus 9, minus 7, minus 3, x1, x2, x3. So this is the x dot is equal to ax plus bu form. This is the state equation. And y is equal to cx plus du. In the y, no u term is there. That's why d is 0, and c is 8x1 plus 6x2 plus 5x3. So that's why 865 x1, x2, x3. That is the point, right? And next, so second problem you can do the same as s square plus 3s plus 3 I have given here. I have given answer for your reference, right? So up now what we have discussed, right? We have discussed how to write the state space model for the differential equation, and also we have seen how to write the state space model for the transfer function. We have seen two things. And also the method what we have seen is the direct decomposition method, right? And next we'll see how to get if you next is reverse. Reverse means they'll give the state model to you. That is ax plus bu, cx plus du. They'll give directly in the problem. Now they ask you to calculate the transfer function, right? So for that one, how to write? So for that one, first I have derived the equation. How to derive the transfer function if they have given the state space model? State space model means what they will give? X dot is equal to ax plus bu. Y is equal to cx plus du. This is the state equation. First equation is state equation. Second equation is the output equation, right? So how we have to calculate the transfer function from this state space model? So apply the inverse Laplace transform. Apply the Laplace transform on both sides of the first equation. So x dot means one time derivative means s into x of s we will get, right? S into x of s is equal to a into x of s plus b into u of s. That is the derivative of this, Laplace transform of this equation. And also y of s is equal to c into x of s plus d into u of s. That is the Laplace transform of the second equation, right? So that is I am taking 3 and 4 these things. So from these 3 I am arranging this one as taking this ax of s to this side, and I am taking here x of s is common for these two terms, and I am taking x of s as a common here. See, observe here carefully. A is the matrix here. Important. X is a matrix here, right? So if you take the common x of s, then I am writing here identity matrix here, Si minus A, right? Si minus A into x of s is equal to b into u of s, right? Now for this equation, I am going to multiply with Si minus A whole inverse. If I am multiplying with Si minus A whole inverse this side, right? This 2 A inverse into A like that, right? It will becomes 1, right? The matrix will become 1, and into x of s is equal to here Si minus A whole inverse into b u of s. See, now what we require is we require the transfer function. Transfer function is nothing but the here x of s is equal to, right? So this becomes 1. It is Si minus A whole inverse into b into u of s. See, but what we require the transfer function from the state model, right? Right. So transfer function means we require y of s and in terms of inputs, right? Y of s is the output, u is the input, right? So you require that equation. That's why here I am taking this equation again here. This equation and substituting this x of s place in this y of s, what you will get? You will get the relation in terms of output is equal to input. Input is u of s, output is equal to input, right? So I am taking common u of s as an input here. Now the transfer function is equal to output by input, that is output y of s by input u of s, that is equal to c into Si minus A whole inverse into b plus d. So this is the transfer function. See, they will give the A matrix, B matrix, C matrix, and D matrix. They'll ask for what is the transfer function. So the formula for the transfer function is y of s by u of s is equal to, that is output by input is equal to c into Si minus A whole inverse into b plus d. This is the transfer function equation. The derivation is also important. This derivation, right? Now we'll see one example. So they'll give the state model. That is, state model means they are giving the A matrix, B matrix, C matrix, and D matrix. So from those matrices, you have to write the transfer function. That is simple. By using this simple multiplication of matrices. So determine the transfer function from the state model, right? X is equal to ax plus bu, y is equal to cx plus du. So A, B, C, D. See, observe here to derive the transfer function, what are the matrices you require? A matrix, B matrix, C, D. Right. So first identify the A matrix, B, C, D matrices. So this is the A matrix, and this is the B matrix, and this is the C matrix, and this is the D matrix. So they have given D as 0. They are not giving anything in between. See, they have given only this thing, and they are not giving this one, means they are assuming D is equal to 0 matrix, right? Remember that point. So from this A, B, C, D matrices, how are the transfer function? Transfer function is equal to C into Si minus A whole inverse into B plus D is the formula, right? A inverse is equal to adjoint A by det A, you know this one, right? So here Si minus A whole inverse is equal to adjoint of Si minus A by det of Si minus A is the formula, right? So first of all, you have to calculate what is this one, adjoint A by det A. So first of all, that one, Si minus A, I am calculating. What is Si minus A? I means 1001, right? So 1001 multiplied with S means S00S is the matrix, right? Minus A means already given in the problem 03 minus 2 minus 5. If you subtract these two, you'll get S minus 3 minus 2 s plus 5. Now what is adjoint of Si minus A? Adjoint of Si minus A is, right? So ABCD is the matrix. Then for 2 by 2 matrix, it is D minus B minus C A. So that's why I'm writing here D. This one S plus 5 is D here, minus B minus C A here. So here observe this one, signs are reversed. So this is adjoint of A. Now adjoint A by det A. So determinant of Si minus A is equal to, see, for 2 by 2 matrix it is B square minus 4AC. I mean, sorry, this is det Si minus A means AD minus BC, right? S plus 5 into S minus 3 into T, 3 into minus 2. So that is, you'll get S square plus 5S plus 6. If you write this one in the fractions form, it is S plus 2 into S plus T. So that is, you will get this one. So up now what happened? Adjoint A by det A you got. Now this adjoint A by det A should be multiplied with the B, and the result again should be multiplied with the C, and then you have to add the D matrix, right? So that's why here this adjoint A by det A is multiplied with B, C, right? And that should be added with the 0. D is 0 in the problem, right? Now we have to multiply this. So I multiply first these two. S plus 5 into 1 plus 3 into 1, 3. S plus 8. Next here. S plus 5 into 1 plus 3 into 1. S plus 8. Again, minus 2 into 1. S minus. So right here. Minus 2 plus into 1 plus S into 1. So S minus 2. So this thing is going to multiply with 2110 again. Right. So multiplying this one. Similarly here. 2 into S plus 8 plus 1 into S minus 2. Similarly 2 into S plus 8 plus 1 into S minus 2. So you'll get these things, right? So here denominator is S plus 2 into S plus 6. You can give this term to all individual elements here. So now this is the transfer function. So what is this transfer function indicates? Output and input relation. See, it is y1, y2 is equal to this one into u1, u2. See, 2 inputs are there, 2 outputs are there, right? So what is y1? y1 is equal to 3s plus 14. This one into u1 of s plus 3s plus 14 by this one into u2 of s. That is, the output y1 depends upon both inputs here. That is multiple input, multiple output system here. So that is the way we have to write the transfer function by using the state space model, right? Similarly here, second problem for your tutorial, A, B, C, D matrices ichcharandi. So by using the same formula, you have to derive the transfer function. So up now what we have derived? State space model ela rayali. They have given the differential equation, how to write the state space model, and they have given the transfer function, how to write the state space model by using the direct decomposition technique we have seen. Later we have seen they have given the state space model, how to write the transfer function, now reverse. So that thing by using the C into Si minus A whole inverse into B plus D formula. By using that one we can write the transfer function from the state model, right? So here we have covered 4 important problems. Now we'll see. So compute the state transition matrix, right? See, state transition matrix formula is e power at is equal to Laplace inverse of Si minus. దీనికి Laplace inverse చేయాలండి. This is a state transition matrix. In the problem they will ask, they'll give the ax plus bu plus cx plus du, they'll give in the problem state space model, but we don't require BCD matrices there, we require only A matrix, right? So for calculating this state transition matrix, so compute the state transition matrix if A is equal to 0, 1, minus 2, minus 3. The formula is e power at is equal to this. E power at is nothing but a state transition matrix. So how we'll get this one is Laplace inverse of Si minus A whole inverse. What is Si minus A whole inverse? It is nothing but adjoint A by det A. So you can write Si minus A here, and Si minus A whole inverse is equal to adjoint A by det A. So det A you can easily calculate. It is nothing but AD minus BC, right? So it is S plus 2 into S plus 1 will get here. Now distribute this term to all the elements here. So now we have to apply the Laplace inverse to this term, Laplace inverse to this term. So right. So now how we have to simplify Laplace inverse of this one? How we are writing means here you have to write the partial fractions here. S plus 3 by S plus 1 into S plus 2 is equal to A by S plus 1 plus B by S plus 2. Now we have to calculate the A and B, their constants. After that one, apply the Laplace inverse. Then you'll get 2 into e power minus t. E power minus t is the Laplace inverse of 1 by S plus 1 here. S plus 1. S plus 2 is e power minus 2t is the Laplace inverse of those two. So like that. So do the partial fractions for these 4 terms and apply the Laplace inverse. You'll get the time domain matrix. This is the state transition matrix calculation from the given state space model. So this is the tutorial problem. You can get the solution for this also, right? So right, again I'm repeating this one. What is the state transition matrix, right? The state transition matrix, right? E power at can be written as L inverse of Laplace inverse of Si minus A whole inverse. So that is in the problem examination, they'll give a x dot is equal to ax plus bu, y is equal to cx plus du, right? But you don't require C matrix, B matrix, D matrix there. You require only the A matrix, right? So from the A matrix, right? So from the A matrix, you can write Si minus a whole inverse. If they'll give no problem or they won't give no problem, right? So A matrix is sufficient for us. So Laplace inverse of Si minus a whole inverse. Si minus a whole inverse is nothing but adjoint A by det A. So you can calculate adjoint A by det A. Apply the Laplace inverse here. So here how to get the Laplace inverse of this one is by using the partial fractions. S plus 3 is equal to A. S plus 3 by S plus 1 into S plus 2 is equal to A by S plus 1 plus B by S plus 2. You can calculate the A and B constants and then apply the Laplace inverse separately. You'll get the 2 into e power minus t into 2 into e power minus t minus e power minus 2t. So like that you'll get the all the Laplace inverse for all the terms. So this is the state transition matrix. So you can solve this one. So next important concept is the controllability and observability. See, a system will be given you, and you have to write the controllability and the observability, right? Whether the system is controllable or whether the system is observable. How to calculate that one, right? So a system is said to be controllable if the rank of matrix, right? See how the system is said to be controllable or observable. See what is the system we are talking? We are talking the system means we are talking the state space model of the system is available. Ax plus bu, Cx plus du is available, right? From that A, B, C, D matrices, we have to write that whether the system is controllable or observable, right? A system is said to be controllable, right? If the matrix B, AB, A square B, so on up to A power n minus 1 into B is equal to the order n. Is equal to the order n means what is order n here? N is nothing but the order, that is highest differential equation, right? Highest order derivative, right? See, it is equal to order, I mean the rank of this matrix is equal to order n means, right, the determinant is not equal to 0. That is the simply the matrix B into B is B as the first column, A into B as a second column, A square B as a third column, so on up to A power n minus 1 into B as a last column, right? If you do the derivative of this one, if the derivative is not equal to 0, right, then we can say that that is controllable. And how can say that one is observable means completely observable? C transpose, A transpose into C transpose, so on up to A transpose whole power n minus 1 into C transpose. So this matrix determinant is not equal to 0, then you can say that one is completely observable. That is for controllable you require B and A matrices. A comma B matrices are enough to observe the controllability, right? So, right. For observability, C and A matrices are enough, right? You don't require BD here, right? So now we'll see first problem. A matrix is given and B matrix is given. Now we have to write the controllability, right? What is the formula for controllability? The matrix is B and AB. Here A is the 2 by 2 matrix, so that's why n is order is 2 here. If n is 2 here, A power 2 minus 1 into B is A into B. That is the last one is AB only. That is B into AB. B as the first column, AB as the second column of the matrix. Now we have to write what is this matrix, and then we have to do the derivative of this. We have to do the determinant of this matrix. If the determinant is not equal to 0, then we can say that the rank is 2 and it is controllable, right? So for that QCR, I mean the matrix is equal to B. What is the B here? 0, 1. So I'm writing here 0, 1 here in the matrix 5C, 0, 1 I'm writing here. And what is the second column? How you will get? A into B is the second one. So what is A into B? A is in the problem given 1, 1, 2 minus 1, B is 0, 1. So multiply this A into B, you'll get 1 minus 1. Now this 1 minus 1 can be written as the second column of this matrix. So this is the first column and second column. So now we have to get the determinant of this matrix. That is AD minus BC, 0 into minus 1 minus 1 into 1. That is equal to minus 1, which is not equal to 0. That's why the rank of this matrix is 2, which is equal to order n, that is 2. So it is controllable. The system is controllable, right? And you can check this A and B problem, tutorial problem, right? And next, coming to the observability, right? Coming to the observability. Observability means A matrix and C matrix is enough. That's why I'm giving only A and C matrices here. We don't require the B, D matrix. So the formula is C transpose. Second column is A transpose into C transpose, so on up to. Here n is nothing but the order. Here A is 2 by 2 matrix, so n is 2 here. N is 2 here. So that's why if n is equal to 2 here, 2 minus 1 is 1. So that is C transpose as the first column, and the next column is A transpose, C transpose is the last one. right? So the first one is C transpose. C is given as 1 3. C transpose is so this is 1 3 here like this. So it is 1 3 C transpose. So this C transpose I am writing here 1 3. Next A transpose into C transpose. A transpose is equal to A is given as -1 0 -2 0 -2. So -1 0 0 -2 as the A transpose. A transpose into C transpose will get -1 -6. So how to multiply this one? -1 into 1 plus 3 into 0, that is -1, right? 0 into 1 plus -2 into 3 -6, right? So that is -1 -6 as the second column. So for this matrix I have to calculate the determinant. Determinant is equal to AD minus BC. AD minus BC is equal to -3 will get, that is determinant is not equal to 0 and the rank is 2 here, right? The rank is 2, then it is observable, right? So for the observability the formula is Q0 is equal to C transpose A transpose C transpose so on up to A transpose whole power n minus 1 into C transpose. This is for observability, we require only A and C matrices. Whereas coming to the controllability, you require B, A, B, A square B, so on up to A power n minus 1 into B. Here, B and AB matrices we require for controllability. For observability, we require C and A matrices. These are the two important problems we have in the syllabus. So now overview. What are the formulas we have used, right? So the first one is how to get the transfer function from the state model, right? From the state model, how to get the transfer function. That is formula is C into Si minus A whole power minus 1 into B plus D. Whereas Si minus A whole inverse is equal to adjoint A by det A. Here no, here adjoint A by det A. Here inverse అనేది ఉండదండి ఇక్కడ, right? Adjoint A by det A. Next formula for state transition matrix. How to calculate the e power at matrix, state transition matrix. That is equal to Laplace inverse of Si minus A whole inverse. Already solve the problem on that also. And next one is the controllability and observability. Controllability means the matrix B, AB, A square B, A cube B, so on up to A power n minus 1 B. The determinant of this matrix is not equal to 0, then it is controllable. And observable means C, A transpose into C, so on up to A transpose whole power n minus 1 into C transpose. That is, if this matrix determinant is not equal to 0, then it is we are saying that one as a completely observable, right? So what we have seen now, right? We have seen the first thing, how to write the state space model for the differential equation we have seen. Next we have seen how to write the state space model. They have given the transfer function directly by using the direct decomposition method. And next we have seen the how to write the transfer function. They have given the state space model reverse, right? They have given the state space model. Now how to write the transfer function by using the formula C into Si minus A whole power minus 1 into B plus D. And later we have seen the controllable and observable, right? When we are saying that one as a controllable means, right, B, A, B, A square B, so on, that matrix determinant is not equal to 0, then we are saying that one as a controllable. And when we are saying that one as observable when the matrix C, A transpose, C transpose, so on, A transpose whole power n minus 1 into C transpose. The determinant of this matrix is not equal to 0, then we are saying that one as a observable. And the other thing what we have seen the how to calculate the state transition matrix, right? That is e power at. The formula is Laplace inverse of Si minus A whole power minus 1. So that is to calculate the state transition matrix, you require only the A matrix, right? So by those problems, you can calculate all these things. And we have other important two methods here. We'll see those two things here. That is how to derive the state model by Foster's form. See, already we have seen transfer function ఇచ్చారు. Transfer function ఇచ్చిన తర్వాత direct decomposition method ద్వారా ఎలా కనుక్కోవాలో చూసామండి ఇందాక. So ఇప్పుడు another two methods are there. They have given the transfer function here. We have to write the state space model by Foster form, right? So while solving the problem in the examination, you have to carefully observe. So which form they will ask, right? So previously that one is the direct decomposition form. Here the Foster form. So Foster form is it is nothing but a canonical form. So first of all, the given function or given transfer function is written in terms of partial fractions like A by S plus 3, B by S plus 2, C by S plus 7. So how to do the partial fractions for this, right? So you'll get A constant, B constant, and C constants here, right? So A is minus 1 by 4, B is 2 by 5, C is minus 3 by 20, right? So now here what I am doing here is, right? So see, this is the matrix, right? But here observe this one, y of s by u of s is this one, right? Right. But y of s is equal to u of s into this one. What is u of s? U of s into this one, y of s is equal, right? So y of s is equal to this total thing into u of s, right? See here, observe carefully here. Yes, I have taken the common here. See here, s plus 3 is there. Yes, I am taking common here. So 1 plus 3 by s here, 1 plus 2 by s here. That is, see, all of you are able to understand this one, right? So a, b, c are obtained from the partial fractions. Here, just taking common s here, and here u of s is directly taken to here. So that is u of s is given to these three terms. So I am taking this s to the numerator, right? So 1 by s into 1 by 4 by 1 plus 1 by s into 1 by this 3 by s I am writing as 1 by s into 3 here. So like this I am writing for all these three terms. See why I am writing this one is, see, observe here carefully this one. It is g of s by 1 plus g of s into h of s form. G of s is 1 by s, g of s by 1 plus g of s into h of s form. So that is right. See, for negative feedback we can write the function. For negative feedback I can write the function g of s by 1 plus g of s into h of s for this block diagram, right? So for this term I am writing this one. So 1 by s here, and negative feedback gain is 3 g of s, right? So for this block it is g of s by 1 plus g of s into h of s, but that is multiplied with 1 by 4 here. So that's why the output this one here. That is the, for this block we will get g of s by 1 plus g of s into h of s, that is multiplying with 1 by 4. So you'll get this term, and this term is adding with the second term. This term is g of s by 1 plus g of s into h of s. So that's why here g of s by 1 plus g of s into h of s you'll get by using this one, and that is multiplied with 2 by 5. So 2 by 5 I'm writing here, right? So like that, this second term you'll write here. So here minus is there, that's why I'm writing here minus. Here plus is there, I'm writing my plus is here, and here minus is there, I'm writing here minus. So this is the diagram I have constructed from this one. After constructing this diagram, we have to write the assume the states. Here x1, x2, and x3. If it is x1, it is x1 dot. If it is x2, it is x2 dot. If it is x3, it is x3 dot. These are the assumptions here, right? So from this one, x1 dot is equal to, it is output of this adder. That is, one input is u of s. So u of s minus 3 into x1. Right, minus 3 into x1 is coming here, and from here it is u of s. So that is x1 dot is equal to minus 3x1 plus u. So similarly x2 is equal to minus 2x2. Here u of s you will get. So x2 dot is equal to minus 2x2 plus u. Similarly x3 dot is equal to minus 7x3 plus u. Minus 7x3 plus u. So that is x3 dot. So why you are writing these equations? So similarly the output y is equal to, y is the output of this one. So x1 into 1 by 4 minus x1 into 1 by 4 plus x2 into 2 by 5 plus, or minus x3 into 3 by 20. That is the number y of s. So that is y of s is equal to minus 1 by 4 x1 plus 2 by 5 x2 minus 3 by 20 x3. So that is, from these three you can write the state equation. From this one you can write the output equation. So x1 dot is equal to minus 3 x1. So x1 unandi ikkada minus 3 into x1, migitha rendu zeros, and u also is there, though that's why it is 1 into u here. Similarly x2 dot is equal to minus 2 x2, x2 దగ్గర minus 2, and next u is there, that's why it is 1. x3 dot is equal to minus 7 x3 plus u. So minus 7 is in the place of x3, right? See why? Because x3 dot is equal to 0 x1 plus 0 x2 minus 7 x3 plus u will get. So this is a state equation for this, from these three important equations, right? So next output equation is equal to minus 1 by 4 x1 plus 2 by 5 x2 minus 3 by 20 x3. That is the point you had to write. That is, here in the Foster form or canonical form, right? See, after writing the answer, you'll get the diagonal elements only. The remaining terms are zeros, and also the diagonal elements are nothing but the denominator terms 3, 2, 7. See, 3, 2, 7, right? So these are the coefficients here. Minus 3, minus 2, minus 7 are the like that. We can verify the answer. We can verify the answer after solving the problem in this canonical form or Foster form. Similarly, you can derive derive the same thing here for this problem also, and obtain the state space model. See, given the transfer function. Here they're asking for cascade programming. That is, total three things are there. First one, they'll give the transfer function, ask to calculate the direct decomposition form, and ask to calculate the Foster form, and the third form is the cascade programming form. So that is how we are in the cascade programming form, right? See, for that one I am going to solve here. Okay, no problem. We'll see this one. See, in the cascade programming form, what we are doing is we are going to splitting this one. right? So that is the transformation split into 1 by s multiplied with s plus 4 by s plus 3 into s plus 2 by s plus 1. Like that, we are going to split into groups, group 1, group 2, and group 3. See, s plus a by s plus b will get, see, for this one, the diagram is 1 by s into b. See, similarly, what we have written in the direct decomposition form. First, we have written for the denominator. The denominator is s plus 3 here. So only 1s is there, right? So 1 by s is only 1 by s. So 1 by s into b we have written here. So b means denominator 3. So for this one, we have to add the numerator. Numerator is here, the coefficient is 4. That's why here it is 4 and here it is, right, 1, the coefficient of s. So that is, so this is a block diagram for this one, s plus a by s plus b. And 1 by s plus b, the block diagram is this one, already we have seen, g of s by 1 plus g of s into h of s. That is, after splitting like this, you have to write the diagram for this one, right? See, s plus 2 by s plus 1, the diagram is this one, s plus 1, the denominator, and for the numerator 2 we are writing here, and here it is 1. No, nothing is there means it is 1. So this is so from this one we are going to generate the s plus 2 by s plus 1, s plus 2 by s plus 1, and the output of that one is multiplied with the second one. Second one is s plus 4 by s plus 3. So the denominator is 3, numerator is 4 here, right? So here 1 by s is there, right? Now here at every 1 by s, output we have to assume the states. Important point. Output of 1 by s, you assume the states first. That is, here x1 I am assuming output of 1 by s. X2 I am assuming at the output of 1 by s. And x3 I am assuming as the output of 1 by s here. X1, x2, and x3 I am assuming here. Right. If it is x1, then if it is x1, then the input of this integrator is x1 dot. If it is x2, it is x2 dot. If it is x3, it is x3 dot. You know this one. So from this one, we'll write the what is x1 dot. X1 dot is equal to, right, 4 into x2 plus x2 dot. Right. 4 into x2 plus x2 dot. Similarly, x2 dot is equal output of this adder. Output of this adder is nothing but, right. So here it is 2 into x3, and this term is output of this adder. That is u of s minus x3. So that is x2 dot is equal to this one, and x3 dot is equal to this one. So like this, from this diagram we are going to write the x1 dot, x2 dot, x3 dot. But the point is the actual state space representation is x1 dot is equal to ax plus bu. Only x terms undalandi, derivative terms undakodu ikkada. So that is, you have to convert this x2 dot in terms of x1, x2, x3 only. How we can write that one? Right, how we can write that one is, so from these three equations, if you substitute 3 into in x3 dot place, you can write this one. It will convert this one into x2 and x3 only. X2 dot is equal to, and again this x2 dot you will substitute in x1 in first equation, you get x1 dot is equal to u of t plus x2 plus x3. That is, now we can return in terms of ax plus bu. X1 dot is equal to. Similarly, you have to write for x2 dot and x3 dot. Right. So now we have written the general form. X1 dot is equal to ax plus bu. X2 dot is equal to ax plus bu. X3 dot is equal to ax plus bu. Now we can write the matrix form. Now what is y? Y is nothing but here. Y is nothing but the x1 here, right? X1, right? So y is directly writing as x1 here. So from this equation we are writing the state space model, right? So u of t is there. So that's the 3 ones, and it is x2, x3 is there. So these 2 ones, and here x2, x3 is there, minus 3, minus 1, and here only x3 is there. That's why it is only minus 1 here. Means the remaining all are zeros, right? And y is also only x1 is there. That's why the remaining terms are zeros here. So this is another method of, this is called cascade programming method, right? And see, this problem is important tutorial problem. All of you carefully solve this one. Maybe in the exam, this problem may appear in the second mid also. So why? Because here I have written simple. So s plus 6, s plus 5, s plus 4, s plus 3. So I was writing it. I am taking s plus 4 by s plus 3 as one group. So that's why 3 here, 4 here. S plus 6 by s plus 5 another group here. So 5 here and 6 here. Now we can assume here. So where 1 by s is there, here 1 by s is there. So here x1 we have written, and next 1 by s is here, and here I am writing x2 here. If it is x1, you can write this one as x1 dot. If it is x2, you can write this one as x2 dot, right? So from this one, you can write what is x1 dot and what is x2 dot from this equation. I have already given this one here, but in this x1 dot is equal to ax plus bu, actually syntax, but here x2 dot is there. That's why first we have to complete this x2 dot by substituting minus 5 x2 plus u in this place. That is substitute 2 in 1. You can get x1 dot is equal to, you can get x1 dot is equal to in terms of ax plus bu form, right? So x2 dot is already in that form, and x1 I mean, I already have written here, x1 dot is equal to this one by substituting 2 in 1 here. And x2 dot is already in this form, right? x1 and x2 are two things we have. And also y is equal to this output, y is equal to 4x1, right? And x dot plus x dot. But output equation y is equal to syntax, y is equal to cx plus du. Here x1 dot should not be required here. So that's why here first the x1 dot, you substitute this one, and also x2 dot in this place, we substitute these two. So substitute these two, you'll get the final answer here. So this is the problem important. Carefully solve this one, right? So this is about the 5th unit. I have covered maximum 95%. I have covered the 5th unit, right? You can solve these problems. So I am recording this video, right? I'll share this video to you people so that you can cover total unit in the single class, right? I'm going to stop the recording.